Hello everyone, my name is Tingyu Wu, and today I'm going to talk about latent consistency model and its application in image generation. The reason that I would like to choose the LCM is that the latent diffusion models, as the most popular model, has achieved remarkable results in synthesizing high-resolution images. However, the iterative sampling process is computationally intensive and leads to slow generation. Moreover, the applications to the conditional diffusion model and the incorporation of the classifier-free guidance have not been explored, rendering their methods unsuitable for text-to-image generation synthesis. My main goal is to use less time to generate high-resolution and noise-free images. Now let's talk about the reimplementation details. First of all, this reimplementation was based on the diffusion model, and I reimplemented the encode prompt and applied it to the LDM with given algorithm in the next slide. I checked the classifier-free guidance, and I also applied the multi-step latent consistency sampling algorithm. Now let's talk about the algorithm. This is the multi-step latent consistency sampling algorithm. It's very similar to the one in consistency models, except the incorporation of the classifier-free guidance in LCM. The latent consistency models directly predict the origin Z naught of the augmented PF-ODE trajectory given the guidance scale omega. Sample quality can be improved by alternating the denoising and noise injection steps. In particular, in the nth iteration, we first need to perform noise injecting forward process to the previous predicted sample Z, where tau n is a decreasing sequence of time steps. This corresponds to going back to the point of Z hat tau n on the PF-ODE trajectory, then perform the next Z naught prediction again using the train the latent consistency function. Let's evaluate the model. Obviously, given the picture on the right, the modified features worked perfectly on the pre-trained models. Time to generate the image was reduced to 2 seconds on average. However, this is not guaranteed. It could be changed with the steps of inference. High-resolution image generated with noise-free when increasing the steps of inference. As to the pictures on the right-hand side, I used the keyword the Great Wave of Kanagawa. The first set uses 1 step of inference. The pictures are very blurry, but you can still see that they are waves. And the second set of pictures uses 3 steps of inference. And now the pictures are very clear, and the original pictures can be seen from them. And the third set of the images does the same, but adds more detail to it. And as to the last set of pictures, it uses the 8-step inference, which reflects the detail, light and shadow, and even the seal of the original picture if you take a close look at it. However, the trade-off is the longer generation time. This time, it took about 10 seconds to generate 4 pictures. However, this also meets my expectations. As to the results, I compared the 2 outputs. The first set is from the LCM model, and the second part is from the LDM model. Notice that both models are trained with LAI-ON5B datasets, which align with the particular and popular aesthetics. Both sets of images are on a 4-step inference guidance scale set to 6.5. Although we can still see that the lower set of pictures meet the text input description, but it still has lots of noise as well as lack of photorealism. This part is still far away from my expectations. And thank you for watching my presentation.